Welcome, 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 guys. So we're here to talk about names and formulas. So this is lecture 4, and we're going to pick up where, kind of where we left off. So we're going to go with names and formulas today. If you have any questions from what we've talked about previously, please let me know. And let's see what we can do with names and formulas. So we're going to talk about compound types, ionic compounds, molecules and molecular compounds. We'll talk about empirical formulas, and then we'll talk about naming. So those are our general topics for the day. All right, review from last time. I want to know, what are the most stable electron configurations for magnesium in the following forms? So I want the full notation, the noble gas notation, and our most stable ion. So I'm going to ask you to take a break here. I'm going to ask you to write all 3 of those notations down. And then I'm going to go through all 3 of those answers for you. Now, in order to do that, I'm going to have to pull over my periodic table. So I'm going to go ahead and rearrange some things on my screen while you do that. And please take some time, pause here, and let's make sure we come back with that. So. Okay, so we want to talk about magnesium. Magnesium is this guy right here. He's number 12. Okay, so magnesium is Mg. Again, he's number 12. So we know we're going to be talking about him in his neutral state. So we're talking about 12 electrons that we need to deal with. Okay? So 12 electrons that I need to deal with. Him being in that location right there. I'm going to pull this here. And I'm pull. Sorry. No, that's not what I wanted. This one right here. And there. Okay, so remember what we talked about last time. If we're going to do an electron configuration, we're going to be basing it on where we are in the periodic table. So this first row is a row 1. He only has an S type. We have 2 electrons that can fit in that S type. So that's going to be a 1s2 for that first row. We can also symbolize that as an He core. Okay, beyond that, we do our lithium configuration. So that's a 2s1. Beryllium would be 2s2. Okay, we can then go over to our boron, and that would be a 2p. There would be 1. If we go all the way over to neon, that'd be 2p6. So again, we would then go past and we'd have our 2s2, 2p6. And so if we're talking about that core, we're not talking about our neon core. So that's exactly what neon looks like. So that's everything in and up to neon. We go beyond that, we now are in row 3. It's an S type because we're in the S block over here. So this S block that we've got. And we have 2 electrons that need to go into that 3s orbital. So for magnesium, that'd be 3s2. And so we have 3s2. So this is our full electron configuration where we write everything out. We have our noble gas notation, which includes the noble gas previous. So the neon is our noble gas previous. And then that 3s2, everything is beyond it. And then we want to talk about its most stable ion. Now remember, when we talked about making an ion for magnesium, we said that it wanted to lose 2 electrons. We said that this guy right here would lose 2 electrons to become like neon, right? And so the electron configuration that we would have would either be listed as Ne, or we would list that as 1s2, 2s2, 2p6, or we could explicitly write this as neon 3s0. Okay, and we can include the 3s0 on either one of those to indicate that we've lost those 2 electrons. Now, all of those are considered correct. So again, we can have Ne by itself, We could have any with a 3s0, that's this one over here, 1s2, 2s2, 2p6 with a 3s0, or 1s2, 2s2, 2p6. And all four of those represent Mg2 plus, which is what will happen when we take those two 3s electrons off to make it look like the nearest noble gas, which is neon. Okay, so cool with that. All right, so let's not forget that when we take electrons away, we take them from the thing that's the furthest out, either the last thing that we filled, or the furthest from the nucleus. So when we get down here and we're talking about adding things to this 4s and the 3d, we always take from the 4s first, and then the 3d, because the 4s is further from the nucleus, so we'll take from the 4s first. Okay? Questions, comments, problems on that? All right. So that's our situation for that. Okay. All right. So when we were talking about our table, I mentioned to you that there are metals, which is all of these guys over in here, and we had nonmetals, which is all of these guys up in here, right? So there's metals and there's nonmetals. Metals are most of the table, nonmetals are the upper right corner of the table. And it's important to understand that because the metals and the nonmetals, when they bond with other things, it determines what kind of bonds they make. Okay, there are two different types of bonds that we can make. We can either make a covalent bond, or which then makes a molecular or a molecular compound. Oh, and that's made between nonmetals and nonmetals. So if I'm talking about stuff that's up in this corner, so we've got like carbon and oxygen. So we can have CO, that's a nonmetal to nonmetal bond. That's a nonmetal to nonmetal. And so that's a covalent bond. Okay. For right now, all we're going to say is that's a covalent bond. We can also have a metal to nonmetal bond. So if we talk about any of these metals over here, we could talk about like magnesium, right? We could talk about magnesium bonding to oxygen. Okay, and I know that magnesium is a metal. He's a 2 plus. Mg is a 2 plus ion. I know that oxygen can pick up 2 electrons to become like the nearest noble gas, which is neon. And so if I put those two together, I get an MgO. And that's a metal to nonmetal bond, which is an ionic bond, and it therefore makes an ionic compound. Okay. What you'll probably see from those two things is that they're a bit different. When I talk about making a covalent bond, I wasn't worried about what the charges were. When I talked about making a metal to nonmetal bond, I was worried about what those charges were. And I needed to make sure that I had the same positive charge as I had negative charge. Now that may not have been obvious because I intentionally picked something that was a +2 and -2 to put them together. But if I choose something that's not Mg2 plus to put with my O2 minus, then we have to worry about that, right? So what if I pick something that's an alkali metal instead of an alkaline earth metal? So what if I say, okay, let's talk about Na, which happens to be a +1, right? And I want to put that with that O2 minus. I still need to make a neutral compound. So I need to have as many positive charges as I do negative charges. In order to make that work, I need to have 2 NAs for every oxygen. And so what I'd have is Na2O. Okay. So what I see is that since this is a 2 minus and this is a +1, the charge here becomes a subscript here, and the charge here becomes the subscript on the O. Okay, so they're cross multiplied, all right? And so that determines how many of each of those I have. So our metal to nonmetal bonds, those ionic bonds and the ionic compounds, we need to be concerned about the overall charge on those molecules. So as long as it's an ionic compound, it should be neutral. Now, if it's an ion, if it's a polyatomic ion, it may have an overall charge. That's true. Okay, but we can talk about that a little bit later because we typically find those in our exam handouts, and then we can see what that overall charge for that species should be. When we talk about our covalent compounds, we are putting them together in whatever combination has been dictated to us, which is typically dictated by the name of that component, right? So we'll talk about that when we talk about our nomenclature. So it will tell us how many of each there should be. They can come together in lots of ways, and you probably already know this, but you don't know that you know. We can talk about carbon monoxide. So carbon monoxide means that I have carbon bound to a single oxygen. But I can also have carbon dioxide, where I have carbon bound to two oxygens. So carbon monoxide is here, and carbon dioxide looks like this, where I have two oxygens for each carbon. Okay, those are two completely different components, two different compounds with different compositions. Okay, so I have one carbon for both of those, but I have twice as many oxygens in the carbon dioxide as I do in the carbon monoxide. Okay? And the names are different because of that. Okay. Questions, comments, problems on our compound types, which is based on what we have bound together and how we make those things, like how they come together and what we're worried about when they come together. Okay. This will become more obvious as we continue to do this. All right. So we have two different types of compounds made from metals and nonmetals, ionic, or nonmetal to nonmetal, which is covalent. Okay. So our ions and ionic compounds. Remember, we talked about ions, and ions are things that have either lost or gained electrons. So they have charge on them. Okay. We know that they have charge on them because they either want to lose electrons to be like the nearest noble gas, or they want to gain electrons to be like the nearest noble gas. Okay. So it depends on where they are. If they're metals, then like if I'm a sodium, the nearest noble gas to me being number 11 right here, the nearest one to me is number 10, which is neon. And I have one additional electron compared to neon, so I want to lose that electron to become like neon. But if I'm over here and I'm a nonmetal, and say I'm chlorine, right? I have 17 electrons. I could lose 7 of them to become like neon, or I could gain 1 more to be like Rl. And it's way easier and way more favorable for me to gain an electron than it is to lose 7. Okay, it's much harder to pull off 7 of them than it is to gain 1. Okay, so that determines whether I lose or gain. It's the position in the table and how easy it is to get to that nearest noble gas. All right, so we're either going to gain electrons or lose electrons to become like that nearest noble gas. Okay, the charges appear as superscripts on the left-hand side of the atom name. So, whatever symbol we're talking about. If we're talking about sodium, it'd be an Na. That's his symbol. He would have his charge up here. So we use a +1 because he's in this group right here. He's an alkali metal. So he's going to lose 1 electron to become like the nearest noble gas. So if he's an 11, he'll lose 1 to have 10 electrons, just like neon. Okay. Ionic compounds are formed between metals and nonmetals, and they both become ions, and they're mixed in fixed ratios based on what the charges are. Okay. So if I have an Na plus and I mix it with an F minus, then I have an N, A, and F. Since it's a -1 here and a +1 there, I need 1 of each to make an NaF, and that's neutral. If I have an Na plus, like we talked about before, and I have an O2 minus, then I need twice as many Na pluses as I do the O2 minus. So I end up with an Na2, so that charge there becomes a subscript here. and my charge here becomes a subscript on the O. So Na2O has the same amount of positive charge as I have negative charge. Okay, so that determines what the ratio is between the positive and the negative. Okay, I always want it to equal 0. So here I have +1, -1, and that's 0. Here I have 2 times +1 plus -2, and that's equal to 0. Okay, if we just left it as +1 plus the -2, that would be -1, and so that wouldn't work. That's why we need to have 2 of them. That's why we need that 2. Okay, so that's what we're talking about there. Now, when we talk about our ions, if it's a positive ion, it's a cation. Cat, pos. Cat has pos, so cats are positive. Negative ions are anions. Okay, so it's negative, it's an anti, so negative, anti, opposing, so negatives are anions. Okay, so that's how I remember that's how those charges work. All right, so positive ions are cations, negative ions are anions. Is it important that you remember that? Well, kind of, because I'm going to throw those words around like you know what they are. So you'll need to be familiar with those terms. Okay? All right. Now, as we've talked about, we should be able to predict whether something's going to gain or lose electrons based on its position in the periodic table. So let's talk about that. Now, let's talk about lithium. Lithium is right here. He's an alkali metal. Okay, so since he's an alkali metal, then we should be able to talk about how many electrons he's going to lose or gain. Now, since he's an alkali metal, he's going to lose an electron. Metals lose. He's got one additional electron comparative to helium. So he's going to lose that electron to become like helium. So Li is going to become an Li plus. Okay, and he's then going to have a 1s2 configuration left for his electron configuration. Oxygen is over here. He's one of the chalcogens. So he's in group 16. He's right here. He's number 8. Because he's a chalcogen, he is a non-metal. He wants to pick up 2 electrons, 1, 2, to become like neon. So he needs 2 more electrons to become like neon. Neon is going to have a 1s2, 2s2, 2p6 electron configuration. So that's what he wants. Remember that in his native state, he has 1s2, 2s2, 2p4. Okay? So 2, 4, 8 total electrons. If he gains 2 more, he'll then be 10. So he gains 2, that means he's an O2 minus. Gain of 2 electrons, O2 minus. Okay? So that's that guy. Now, let's talk about calcium. Calcium is an alkaline earth metal. So he's right here in group 2. Since he's a metal, and he's an alkaline earth metal, he's going to lose electrons. He's a metal, so he loses. He's going to lose enough to get back to this argon configuration, right? Now, argon has 18, calcium has 20. So he's going to want to lose 2 electrons to become like argon. So 2 electrons, that argon configuration is a 1s2, 2s2, 2p6, 3s2, 3p6. Okay, so again, 1s2, 2s2, 2p6, 3s2, 3p6. That's the argon configuration. And then beyond that, he has 4s2. I lose the 4s2 to become like the argon configuration, which ends in 3p6. Okay, so my Ca has become a 2+. Right? And that's my electron configuration there. Now, my Cl is in group 17. He's a halogen. Okay, so he's in this group that over here. He's one of the halogens. Remember, I told you need to know some of these group names. So alkali metals, which is group 1, alkaline earth metals, which is group 2, chalcogens, which is group 16, halogens, which is group 17, and the noble gases, which are group 18. And notice I've thrown all of those around in the last couple of minutes. So that's why you need to know them. Okay. Now chlorine is a halogen, so he's right here. He has 17 electrons. All right. So for his 17 electrons, we're talking about 1s2, 2s2, 2p6. So that would be 2, 4, 10. 3s2 is 12. And then 3p6 would be 18. He doesn't have 18, he only has 17. So this is going to be 3p5, right? He only has 5 in that p. And I know that because if I'm in this row 3, 1, 2, 3, 4, 5. So he's got 3p5. He wants to gain one more and be that 3p6. That's what he wants. So when he does that, he gets that 3p6 that he was looking for. And so he's a Cl- to become like that argon. Okay. So we can start to see that this is sort of a pattern. Okay. We see that when we're in row 1, we get to be 1s2. When we're in rows 2 or 3, it's a S2P6, S2P6 situation. And that means that we've got the S and the P full, right? So that outermost row has the S and the P full, right? That's how we get a noble gas configuration, is to have that S and that P full, right? We call that S and that P, that 8 electrons, a stable octet, right? So that's what we're looking for, is trying to get to be that noble gas configuration, all right? So we're always trying to get to be that nearest noble gas. Questions about that? So hopefully not. That's what we're trying to do. Remember, you're always trying to get to be the nearest noble gas. The question becomes, which is the easier way to do it? Now, again, not everything can do that. Carbon has a really hard time because he's either going to have to pick up 4 or lose 4. And neither one of those is very easy for him to do. So it's not very common that he's going to lose either one. And that's why he's a nonmetal and he tends to not get a charge. He tends to be in a nonmetal to nonmetal bond, and therefore he's doing something other than losing or gaining electrons. When we talk about our nonmetal to nonmetal bonds, they tend to be sharing their electrons. Okay, so they're not transferring them, they're sharing. Okay, so questions so far? All right. So I want you to predict the charge on the following guys. So I want you to find sulfur and S and SR and K and F and Ca and N and I and Ba and Cs and Se in your table and tell me, 1, what charge do you think you'll have? And 2, how many do you think it'll be? A 1, a 2, whatever. All right, so that's what I want you to do. I want you to take a break and figure out what you think those charges should be. All right, we'll come back to that in just a minute. Okay, so I need to find sulfur. Sulfur is over here. He's number 16. He's in the non-metal grouping. So he is a non-metal. I can see from his position, he's a chalcogen. He wants to gain 2 electrons to become like argon. So sulfur not only is going to gain electrons, but he's going to gain 2. So he's probably going to be an S2 minus. Since he's right underneath oxygen, I would expect that. I would expect everything underneath oxygen to do the same thing that oxygen does. Okay. All right, well, that's my sulfur. Let's go see if we can find Sr. Looking around, looking around, looking around. I see Sr is over here. He's a metal. So if he's a metal, he's going to lose electrons, so he's going to be positively charged. Since he's an alkaline earth metal, he's going to lose 2 electrons. So he's going to become an Sr2 plus. There's no reason that they're staggered the way they're staggered other than it's easier to read them. Okay, that's all. Okay. Now, is it easy to find these things? Not always. One of the things I'll show you in your exam handouts. Find the exam handout, sorry. Is it may not be that easy to find the things you're looking for on this periodic table. It may be hard. So one of the things that I've provided you with is this table like this. And again, it may be easier to find them in this table. It may not be. So these are all based in atomic numbers order. So you might find them here, you might not. Sometimes it's easier for me to find them here, sometimes it's not. So, you know, if I'm looking for Sr, I only know where he is because he's over here. So he's 38, so I can see he's right there. And he's Sr and he's strontium. My periodic table, sorry, 38 Sr strontium. So on the table that I have here, if I was having trouble seeing him, 38 Sr strontium, I may not necessarily be able to read the strontium. It's very small on this thing, so I can see it here because it's actually bigger than it is on my piece of paper. But you might have an easier time reading the name from this table than you do from the periodic table that's there. So that's the other reason that it's there. One other thing that I'll tell you is that there are 2 masses listed here. One is the one that's in ALEKS, okay, and one is the one that's on your periodic table. So you can use the periodic table masses on the test, and the ALEKS mass is there for you to use when you're working in ALEKS. Okay, so those are the masses that come directly from ALEKS so that you can work with them when you're in ALEKS. Okay, just so you can practice using them. Okay, so there's that. Woohoo! All right, so again, strontium, alkaline earth metal. So he's going to lose electrons. He will lose 1 and 2 to become like the nearest noble gas, which is krypton. So he's going to be a 2 plus. All right, potassium is right here. He's number 19. He's an alkaline metal, so he's going to lose because he's a metal, and 1 because he's 19. So if he loses 1, he'll become like argon. So he's going to be a K plus. Next one we wanted to look at was fluorine, F. Fluorine is number 9. He's a non-metal, so he's going to pick up an electron. He picks up 1 because he's a halogen, and so he becomes like neon because he's picked up that 1 electron. So he's an F minus. Ca is a metal. Calcium is a metal. He's right here. He's an alkaline earth metal. So he loses electrons and he loses 2 electrons to become a Ca2 plus. Now, nitrogen is one of our nonmetals. He doesn't always transfer electrons, but when he does, he will add electrons and he will pick up 1, 2, 3 to be like neon. So he'll be an N3 minus. I is iodine. He's right here. Because he's a halogen, he'll gain an electron. He's a nonmetal, so he'll gain one to be like Xe, nearest noble gas. So I minus. Ba is a metal. He's over here. He's an alkaline earth metal. So he's going to lose electrons, and he'll lose 2 because of his position. So one to be like cesium, and 2 to be like Xe, so xenon. So Ba2 plus. Cs. Well, I know that Cs is over here. So he's a metal as well. Because he's an alkaline metal, he's in this first column, he's going to lose 1 electron. So he becomes a Cs plus. And then finally, we want to look for Se. So Se is the next thing I need to find. Well, I don't see an Se here. I don't see him here. I don't happen to see him in here. I don't really know what to do with any of these, but I don't happen to see him in here either. He's not there. He's not there. He's not there. Oh, look, there he is. Se, and he's underneath oxygen, so he's a chalcogen. That means I would expect him to gain electrons. He's a nonmetal, and I would expect him to pick up 2 to become like krypton. Okay, so Se is going to be 2 minus. Okay, so again, predicting main group elements. Main group meaning this guy, group 1, group 2, group 13, 14, 15, 16, 17, and 18 are the ones that I would expect us to be able to predict. Those are the ones I would expect us to be able to do. So those are things that you should be able to predict based on their position in the table. Okay? Cool with that. All right. Let's keep rocking and rolling. So, common monoatomic ions. Again, based on position in the table. So group 1A is listed here as 1. Those are all my positive ions that come out of here: lithium, sodium, potassium, rubidium, and cesium. All right. 2A, we've got our beryllium, magnesium, calcium, strontium, and barium. All right. We've got our 3A, which is actually over here. So 3A, we're actually looking at boron. We typically don't see being charged, but aluminum 3+, gallium 3+, indium 3+, and then we get into our TL, which can have multiple charges. So you can have multiples. Some of them can. The next group over 14, again, we don't typically see charges that we predict when we talk about these, so I wouldn't predict these. We talk about our next group over. We can talk about nitrogen having a negative charge. We can talk about bismuth having a positive charge, but we typically don't. I wouldn't expect you to predict that. When we get to our next group over, our chalcogens, these I would expect you to be able to predict as a 2 minus. And then our halogens, these I would expect you to be able to predict as having a -1 charge. Now, you can see that hydrogen is included here as being able to pick up an electron. It can. Okay, so it is one that can pick up from there. And he can appear here in this part of the table when we're considering him for that. Right? It happens. I wouldn't worry about that too much. Most of the time when we see him, he's either a positive charge or a negative charge. Usually we can tell from what he's bound to, what his charge is. So I wouldn't worry too much about predicting what his charge is, because we usually tell that by inspection, i.e. from looking at what else he's bound to. Okay? So questions on that? All right. Now, polyatomic ions. ions. Oh my gosh, polyatomic ions are so much fun. Is it necessary to know polyatomic ions? Well, yes and no. Do I expect you to memorize them? Absolutely not. Will you get a table of them? Almost definitely. Where are they in your table? Oh, they're not that far. Sorry, they're further up. What you'll find on your exam handouts is that there is a table of polyatomic ions. This table should include everything that you see on these slides. Okay. You'll see the cations are listed here. You've got ammonium and hydronium are listed here. You don't see the mercury one or mercurous. Okay, I didn't list that here because we don't talk about it very often, so I wouldn't worry about that too much. And again, we don't talk about it very often, so I wouldn't worry about that. So NH4 plus and H3O plus hydronium are the two positive ones that we often talk about. We have our anions, and there are many, many, many of them. What you'll find is that they're in here in alphabetical order. These are the ones I expect you to be able to deal with. So if I say to you that you need to be able to write a formula for like calcium arsenate, you should be able to look up arsenate and know what that formula is. It will tell you exactly what the formula is. So it's AsO4 3-. So you know what the charge is, you know what the atoms that are in it, and in, you know, how many of each there are. Okay, so you should be able to deal with that based on what you're looking at. Now, one other thing that I'll tell you is that some of these are written the way that they're written, and they can be written in different ways. So like benzoate, you'll see that it's written here as C6H5COO. Benzoate can also be written C6H5COO minus. That's one way, and that's exactly what you see on that table. It can also be written as C7H5O2 minus. So we've just written it in a different fashion. Now, why would we do that? Well, it depends on what we're trying to emphasize, why we write it the way we write it. Okay. Sometimes I'm only concerned about how many of each thing are present. That's why I would write it as C7H5O2 minus. Sometimes I'm more concerned about the fact that it's what we call a carboxylic acid, and that's why I would write it as a COO minus, okay, because it emphasizes that carboxylic acid group, okay. It's typically something we do more in organic chemistry, but it is something that you will see depending on where we pulled this information from, all right. Oh, good Lord. So that peroxydisulfate right here, that 2- should be a superscript. So this right here should be a superscript. So that should be up like that. I apologize. Every once in a while, something slips. And it may or may not be wrong on the version of the handouts that you guys got. Sometimes it gets messed up after I posted it. Sometimes it's fine. Sometimes it's not. I'll verify that and I'll repost this if required. Okay. So I just saw it, so I'll check it. All right. So the polyatomic ions, you should see everything that you're seeing here on here, except for mercury 1 or mercurous. Actually, that didn't work the way I wanted it to. Hold on, I apologize. Why am I editing while I'm trying to lecture? I love it when I do this. Nope, that didn't work. Okay. I'll have to try and fix that later. So I'll do my best to add that mercurous to it. You probably won't get it this term, but I wouldn't worry about it. If it's not on the table, you don't get it. So that is deal with that. So it's gonna take me forever to figure that out. Anyway, so there's that. So ions that you need to know will be available to you on the test. Okay. I wouldn't worry about that too much. You should be able to find them and use them. Okay. So if you're asked to write something, from a name to a formula, you go find the name in the table, write the formula. If you have a formula, you should be able to find the name. Okay. So anything that looks like it's got a bunch of things in it, you would recognize that as a polyatomic ion and go look in the polyatomic ion table. Okay. Now, we've only done predictions for main group elements. So nothing in the D block, nothing in the F block. And it's complicated when we talk about that. Now, what are the charges on those? They can be a lot of things. So they can be +2, because if we take these S's, we can pull those out. And if we lose both of those, then it's a 2+. But we could also lose some of the D's that are here. Okay, that's possible as well. And we may just lose one of the D's. We could lose many of the D's. So it can be a lot of different charges. All right. Because we don't know what that charge is, and it could be a lot of things, we usually have to be told. And there are a couple of ways that we could be told that. So it could be in the name. So if I see something that says like lead IV phosphate, then I know that my lead, which is Pb, has a 4+ charge, because that's what this IV means. It means 4. And I know lead is a positive charge, so it's lead 4. And then it's with a phosphate ion, which from my table that I've got over here, I know that my phosphate is listed right here as PO43 minus. So I know I've got my PB4, and my, sorry, it's in my way. I apologize. So PB4 plus, PO43 minus, and then I need to put those two together. So then I have my PB, I need 3 of those, and I need PO4, and I need 4 of those, and that should balance my charges so that I have everything that I need. Okay. So that's what I would be looking at when I talk about that. But that name, this lead 4, indicates the charge on the lead. Okay, so that's one way. If I were looking at this formula right here, this formula would tell me that the charge on lead has to be 4+. Because if it's not 4+, then I wouldn't need to have 4 of the phosphates. And I know that the charge on the phosphate is 3- because that's what's in my table. Okay, so we can look at the charge on the metal from the name. We can look at the name of the compound, which is right here. Okay, we can see the charge on the metal if it's given, if it's written out for us, or we can get inspection. So again, looking at this, I can tell that the PB has to be a 4+, or otherwise I wouldn't get this formula. Okay, so that's what we mean by inspection. Okay, is to work backwards from the formula that I have to tell what the charge is on each of those guys. Okay? So we don't necessarily know what the charges are on any of our D block or F blocks. We have to be told. And so if you're writing a name for something that's a D block or an F block, you need to include the charge in parentheses after that name. If you don't, it is incorrect. Okay, you'll get partial credit for it, but you won't get full credit unless you include that charge in parentheses. Okay, that is only necessary if it's a transition metal. Okay, so D block, F block. All right. So that's a lot of rules. It's a lot of things. So Again, we can find that from the chart on the metal where it's explicitly shown the name of the material. So iron 3, zinc 1, copper 2, or from inspection. So again, if I know O is 2 minus, then if I have 3 O's, that means that it must be an Fe3 plus. If I know that Cl is -1, and there's 1 zinc and 1 Cl, then it must be a zinc 1. I know that O is 2 minus, and there's 1 Cu going with it, then it must be Cu2 plus. Okay, so those are the kinds of things that we're talking about there. And again, if I know that each oxygen is -2, 4 times -2 equals -8. I know the overall is -1, then that means that this chromium has to account for +7 to give you that -1 charge. And so that means that chromium has to be +7 because there's only one of them. So that chromium has to account for that +7 charge. It's weird, it's a little strange, but yes, that is the charge on that particular molecule. Okay, or on that ion. I apologize. On the ion. All right. Cool with that. Questions, comments, problems on what we've done to this point? Okay. So I know that Ca becomes 2 plus, Cl becomes minus, and that means what exactly? Well, I've mentioned that we don't, I mean, I know that positives and negatives don't really stay together, don't really stay apart, right? If I've got two magnets, they're going to be attracted to each other in one way, shape, or form, right? I mean, we may have to rotate them, but they'll come together as long as I allow them to, right? So I know that, positive charges are attracted to negative charges. That happens, and that's natural. So I know that's going to happen. But the question becomes, how do they do that? And I've actually talked about this a little bit. We have to make sure that they come together. We have to make sure that they do so in a way that I have the same number of positives as I have negatives. Okay. So I have to have the same number of positive charges as negative charges. So since I have a Ca2 plus, I need to have 2 Cl minus. And that's to make sure that we have the same number of positive charges as negative charges. Okay, so CaCl2 is the way that that would come together. All ionic compounds will come together so that the overall charge is 0 unless the overall compound has some other charge. So if it's a polyatomic ion and that ion has a charge to it, then we have to make sure that the overall charge equals that of the ion. So Cr2O7 has a 2 minus charge. And so that particular ion needs to have that 2 minus charge. Okay? Cool with that? All right. Ooh. Sorry, yawning. I apologize. I swear this happens when I get on camera. Now, I want you to do some practice at this point. So I'm going to pause, cut off this video, put in a new one while you take a break and figure out what the formulas for the compounds made from the following ions are. So there's a bunch of them here. And I want you to figure out what you think those formulas are going to look like. I'm, like I said, going to take a break. I'm going to cut off this video. We'll start a new one. And then we'll come back together and figure out what these compounds look like. Cool with that? All right. I will see you soon.